Hey everyone, it's Patrick Morrison, and in today's video, I want to address a common misconception about spatial propulsion, which is that the greater the velocity at which the propellant is expelled out of the nozzle of a rocket, the more efficient it will be. Now, it is true that if you increase the propellant velocity, you'll decrease the quantity of propellant mass required to obtain a given velocity for an individual spacecraft. But this isn't the whole story. Let's say that you have two spacecraft, each with a mass of 100 metric tons, that you're accelerating to 100 kilometers per second. Ship A has a propellant velocity of 100 kilometers per second, while that of Ship B is 1000 kilometers per second. Ship A would have to use about 171 metric tons of propellant in accordance with Tsiolkovsky's rocket equation, while Ship B would only have to use 10.5 tons. However, if we look at the energies involved, another story emerges. If you calculate the energy burned by the engines by the kinetic energy of the propellant, Ship A would have used 859 terajoules to get up to speed, while Ship B would have used 5,259 terajoules. And this is where we start to run up against the second law of thermodynamics. Since the engine on Ship B has to expend far more energy to obtain a given velocity, it will accelerate to that velocity at a slower rate, or else it could overheat. So, does this mean the slower the propellant velocity, the better? Well, let's reverse the situation, where we have a third ship, Ship C, with the same mass and target velocity as A and B, but one that expels propellant at 10 kilometers per second. The amount of energy it would have to use to get up to speed is over 110,000 terajoules. So, if we plot the energy needed to get the ship to a given velocity relative to the kinetic energy of the ship against the propellant velocity relative to the final velocity of the ship, we find that there is a most energy efficient velocity at which you should expel your propellant relative to how fast you want to go. This is roughly 63% of your target velocity, at which point, at most, 64.76% of the energy burned by the engine will become the kinetic energy of the ship. Since thrust is a function of mass times velocity, and energy is a function of the mass times the velocity squared, we come to a bit of trade-off in terms of rocket design. High velocity propellants can give you a higher top speed, but they can't accelerate your spacecraft as quickly without melting your engine. So, in simple terms, the greater the change in velocity, the slower the acceleration. This means that when you're considering how to get to another planet, you also have to consider whether your craft will have enough time to reach its top speed. So, when going to a nearby planet like Mars, you'd probably have a lower exhaust velocity, while going to a further one like Neptune, you'd have a higher exhaust velocity, resulting in a slower acceleration. This brings me to an important distinction: fuel versus propellant. Propellant is the reaction mass which you throw out the back to propel your spacecraft forward. Fuel is what you react, or burn, to heat the propellant to direct it out the back at the desired velocity. In chemical rockets, the fuel and propellant are one of the same. But if you were to have a fission-powered rocket, you would have uranium or plutonium fuel rods used to superheat a propellant like water or hydrogen to direct it out the nozzle to drive your craft forward. So, once we enter the nuclear age of rocketry, propellants won't be hard to find in the solar system, and you'll usually be able to restock on them wherever you go. But your fuel, whether it's fission or fusion based, will likely be made up of a very specific combination of elements and isotopes. Odds are a dedicated facility will be required to produce your fuel, and these may not be present at your destination. So, conserving fuel, and by implication energy, will be more important than reaction mass. Alright, that's all I have to say on the topic, so peace out.